Hello everyone. Thanks to everyone for watching this video. My name is Qi Dao. I am an architect and engineer. Today's video is titled Numerical Integration, and it is going to introduce useful methods to compute integration. I am going to give you an overview of what I am covering today's video. First of all, it is a bit of background to the topic, and then focus on the trapezoid rule and the Gaussian quadrature formula before wrapping up with conclusions. Now we are going to give an introduction to numerical integration. A numerical integration in many textbooks is also referred to as numerical calculus, because it is talking about integrals. Here is our problem description, and we will be studying the following problem. Given a function of x defined on an interval from a to b, we want to find an approximation to the integral of this function from a to b. So we will denote this by if, where I stands for integration. F is the function you will be integrating. The interval also depends on the interval from a to b, but we assume that is a fixed constant for this problem. I think all of us still remember. The integral is defined as the limit of the Riemann sum. What is the Riemann sum? The Riemann sum is obtained by cutting up the interval from a to b into many small subintervals. On each subinterval, we simply approximate the function f of x by a constant function, and then we add up the area of these skinny rectangles. In the limit, we let the interval length go to 0, and that is the integral. Before we let interval length go to 0, and what we have would be an approximation to the integral. Our actual numerical integration rules, the main idea behind, it is actually pretty similar to the Riemann sum. We would cut the interval AB into many smaller subintervals just as we did in Riemann sum. And then on each subinterval, we would approximate the function f by some polynomial. Let's denote it as pi over 4, the ith interval and the degree of this polynomial pi. Here is another thing that we can choose and decide. And then the integral of fx on this little subinterval is now approximated by integrating the polynomial pi. On this subinterval, we will add up all these little pieces of integrals to have the integral from a to b, the whole big integral. As we said, the degree of this and the polynomial's pi is something we can choose. It depends on what we need. Now let's take a look at polynomial, starting from polynomial degree 1. This is called the trapezoid. Let's first define the grid. The interval AB is cut into n subintervals, and we denote the grid points as x0, x1, x2, all the way to xn. x0 is A, xn is B, and in between these are sorted. On the interval number I from xi plus 1, we would approximate f by a linear polynomial which we call pi. The polynomial has to satisfy the following property. That is, it interpolates the functions have at the two endpoints. So, at xi as well as at xi plus 1, in the end, these actual results in a piecewise defined interpolation of f. Here is a graphic interpolation. Let's say the interval from xi plus 1 is here. The function f takes the value here. This curved line is my function f. How do I compute the integral from xi plus 1 of my function f? What I do is I approximate this with a straight line that connecting these 2 points on this interval. The integral of fx on this interval is approximated by the integral of pi on this interval, and which we know that the integral equals to the area beneath the graph. In this case, we need to figure out the area of this shaded area, which we see is trapezoid. The integral of pi on that interval from xi plus 1 now simply equals to this expression that is exactly the area of a trapezoid. And then the integral of f over xi to xi plus 1 is now approximated by the integral of pi. And then the whole integral from a to b of my function f is now the sum over each interval and integrating f over each interval. In the end, this is actually a general kind of formula for trapezoidal rule with a generic grid. This is the generic form that is the trapezoid. For special choices of grids, this might take a different form. Next, we will look at something called a uniform grid. We shall be familiar with uniform grid already. We cut the interval a, b to n, equal subintervals. Each interval will have a length h, which is b minus a over n, and the two neighboring grid points xi plus 1 minus xi equals to h for all i's. Then the integral again from a to b of fx, we would use the trapezoidal rule approximated. In the rule, the part xi plus 1 minus xi was simply equal to h. We see that h over 2 is a constant, so we can actually take it outside the summation sign, and then we will be summing over the sum of these two f's with different x index. What I do now is I would like to write out all the terms in this summation sign. We make this observation that many terms actually say term f of xi is actually completed twice. So here, we are thinking of computational efficiency, saving CPU time. We would try to minimize function evaluation. Summarizing all same terms, we see that this expression now simply equals to this one. Now we will take an example using trapezoidal rule. Given a function f of x, which is square root of x squared plus 1, we want to compute the integral of f from -1 to 1 by trapezoidal rule with n equals 4. With the trapezoidal rule written over here, we actually need a value. The function value evaluated at all these grid points xi. Let's set up this table. We set out xi, which ranges from -1 and increase by 0.5 and keep going all the way to 1. And then we evaluated the function value over here. That is the square root of x squared plus 1. The relevant trapezoids are shown in right-hand side. In this example, we have the grid size is h equals to the interval length, which is 2 over 4 equal to 0.5. And then we can simply use the formula, and we get the result is equal to about 2.3251. The exact solution is about 2.2956. Next, we will learn the Gaussian quadrature formula. Let's say AB is a subinterval. So, under subinterval locally, the integration is approximated by the following. There is a set of points xi, so x0, x1 to xn. And there is a set of coefficients a0, a1 all the way to an. What you do is each fxi is multiplied by ai, and you sum them all up. These xi's, they are called nodes, and coefficients ai's, they are called the weight. Typically, in this formula, all the ai's should add up equal to exactly b minus a, the length of the interval. The new idea will be we allow both nodes xi and the weights ai to be adjusted. The reason doing so is I have higher degrees of freedom and could achieve higher accuracy. The nodes xi and the weights ai, they are chosen such that in the end, your rule should give exact value of integral for polynomials of highest possible degree, and let's denote that degree by m. Let's see how this idea can be carried out by considering an interval from -1 to 1. We will start with the simplest case, that is n equals to 1, which means we will have two nodes. We denote them by x0, x1, and two weights a0, a1. The rule should satisfy the following, that is, the integral here should exactly equal to this expression. If f is a polynomial of degree less than or equal to m, now I have to think what is a possible choice for this m. We first observe that if the rule is exact for a polynomial of degree maximum m, then the rule will be exact for all these functions. We actually have exactly 4 unknowns: x0, x1, a0, a1. I needed 4 equations, and therefore the m equal to 3. Before we set up those equations, let's recall this basic integration. Integrating from -1 to 1, x to the power k, what does it equal to? You can find the antiderivative, which will be 1 over k plus 1, and x to the power k plus 1. So evaluate it at two endpoints from -1 to 1. If k is an even number or odd number, we have the relevant results. With that piece information, we can plug in 4 equations and obtain the 4 unknowns. We observe some symmetry is x0 equals to -x1. So the distribution of nodes are symmetric about the origin. And so the distribution of weights are also symmetric. We should take advantage of the symmetry for higher order method, and the symmetry will allow much simpler computation. There is the first Gauss quadrature, and we derive for n equals to 1. This integral is approximated by this expression, and this one will have degree of precision equal to 3, that is, it's exact for all polynomials of power less than or equal to 3. If we increase Gauss quadrature with n equal to 2, this means we will have on 3 nodes, and we denote them by x0, x1, x2, and 3 associated weights with it. The rule would look like this. The integral of f over -1 to 1 equal to this expression. Since the total number of unknown here is 6, this means the rule should give exact solution for polynomials of degree less than or equal to 5. The degree of precision m equals to 5. Here, we will take advantage of the symmetry property, that is, everything shall be symmetric about 0, which means x1 shall be negative value, and it will be exactly negative of x2. And x1, the middle one, must lie on the origin 0, and the weights on x0 and x2 shall be the same. Due to these symmetrical properties, then we already know if fx equals to x to the power of some number, the rule will be automatically exact for all those. Therefore, we only need to check, and if x equal to x to the even power that is less than or equal to 5. We can just solve these 3 equations and obtain the 6 unknowns. Plugging this information in, we can write out our Gaussian quadrature, and it is just this expression here. Similar computations can be carried out to derive from Gaussian quadrature with more nodes. So here is a table for it, and with 1 point, 2 points, 3 points, 4 points, and 5 points. And very often, this can be just coded. Now we will take the previous example using Gaussian quadrature. Given a function f of x, which is square root of x squared plus 1, we want to compute the integral of f from -1 to 1 by Gaussian quadrature with n equals 2. Plug in the nodes and the weights in, we can obtain the result of about 2.2943. The relevant Gauss points are shown in right hand side. This solution is very close to the exact solution, and the computational efficiency is very high. From conclusions, what we learned: the trapezoid rule is a technique for approximating the definite integral. An n-point Gaussian quadrature rule is a quadrature rule constructed to yield an exact result for polynomials of degree 2n-1 or less by a suitable choice of the nodes and weight. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.